Yeah, welcome back to High Performance Computing, Advanced Scientific Computing. So we have today the practical lecture 1.1, which is really a very short introduction to C programming, really having just done in the first part our Hello World C program, which admittedly was very simple, but it carries away the key message what a basically C program entails. It's a text file with basically syntax of C and so on. There's a main function that will be executed and a couple of functions which helps us to bring output and some libraries with a header file. So this is a basic, simple, let's say, idea of a C program. We had then basically a short example of this clustering where I would encourage you to look a bit more into a real C++ program really, which is the HPDB scan open source code for clustering of data. Of course, that is a course that we will look again and again. So it is MPI based, it is OpenMP based. That means it can be computed with distributed memory and also in combination, so-called hybrid programming. And we will look at this in subsequent lectures, also how basically parallel I/O is used and so forth. But with the C program, we learned essentially that we were logging into a system, we can use a modular environment to really check basically what different compilers would be available, what libraries are available. And that's where we found, let's say, HPDB scan. In other words, if you're just interested into basically clustering, you could now go ahead without C programming and of course use the HPDB scan code as is with datasets. Of course, there will be already C programs available. If you go to basically large HPC communities in terms of different sciences and engineering, you will see that they have all their codes already established codes they use again and again. So they, of course, do C programming here and there to augment the codes, C++ programming, or they do even Fortran programming to basically enable, the code with more features and so forth. But these are all advanced topics. We come to these elements when we look a little bit through the application part, which is really the second part of this course, when we go to the neurosciences, terrestrial systems, bioinformatics, and so forth. They all have their programs established. That if you are basically then want to do parallel programming, you will basically do the same steps as we discussed now, basically log into a system. You would have a typical C program in a text file and have to compile it then. Now, we also said that compiling in these environments is okay. So we learned it on a so-called login node, if you remember. And the login node was basically the 5th node on Utun, although Utun had only 4 nodes, which is not really true. In a way, it's 5 nodes, but the login node is sometimes not really counted on, right? So it's basically a helper node to get access via so-called scheduler to basically the compute nodes. And we looked at Newton, we have seen it has 4 compute nodes. They are almost not used because, of course, it's just starting, it's a teaching cluster. If you go to other production systems, of course, this is very different. And this is where we really left the last lecture. So we basically thought, okay, now we have this C program compiled with MPI CC that was running well, no problems. I'll load my modules before that I need. But suddenly, basically, I said to you, be careful with this. And what the point was, when it comes to the execution on a login node, administrators can be basically very angry with you if you do this and overdoing this. Obviously, executing here in the hello world, I just done. It is a very simple, execution, so it doesn't take time on the login node really. It has almost no footprint in the overall system. So basically saying, yeah, this is not a big problem. But if you have, let's say, a running time of an application, which is 8, 16, or 24 hours, maybe, then it quickly becomes a problem because the login node will basically be used by many different users, essentially by all users that have to use a login node in order to get to it, to log into the system. From there, the idea is really to use scheduling and not executing on this login nodes. Hence, when you do this, let's say a big code and want to execute this on a login node for a very long time, just for testing, and let's say all the users of a system would do this for testing, we will see that the performance of the login node would also go down, or maybe even have a problem and fails and so forth. Hence, good practice is rather using a scheduling system and using the login node, obviously for lots of different tasks you can compile usually. Although there are already programs where the parallel aspect is even already in the compilation. This is also possible. But of course, for simple programs like Hello World, that's fully fine. And also in all the assignments of you, it's also fully fine to compile essentially on the login node. But for the execution, we want to learn the proper way. And this brings us to the second part of the lecture today, where we're basically thinking about how to properly use a HPC system. And there, this scheduling is really an important part of it. And we will look into this a little bit into our, let's say, systems that we have in Jülich. You will see there are a couple of systems, not only the deep test cluster we use in one of our assignments, there's also the JUWELS system. And all of them have in common, if you remember from the previous lectures, that they are so-called modular supercomputers. I also looked into this a little bit in the last lecture, and that's why I also want to show you a little bit practice on this. And basically also to understand now this multi-user aspect in it, right? So before we come to the solution and using a scheduler, let's look what is a little bit now the problem if you have a modular supercomputer, many different users. You're basically seeing here systems from the Jülich history coming up to today and the usage in the so-called JUWELS and Eureka systems. And you can imagine that systems with so many flops, we have basically looked at these flops the last time when we basically had said it's a floating point operations per second and the execution. Now, of course, this is not for one single user. So you share these systems always with a lot of different other users. And people usually, and scientists and engineers that want to use these systems, usually also have to firstly get a grant to really access those systems and get computational time on those systems. So it's completely different from the Jotun cluster we have here with 4 nodes. You have multiple nodes, and to access those nodes and to get time and quota on these systems, scientists have to really have scientific proposals for that in order to really then get access to these, let's say, precious systems, because of course, the number of these systems in the world is limited. We talked about the top 500, if you remember. So let's look into that a little bit. Also to get a practical view on this, we said, of course, it is very nice to have access to those systems. And here you have the top 500 list that I was basically alluding to in the introduction, where we have the last list here from November 2021 at the Supercomputing Conference in the US. Usually the top 500 supercomputers are announced. They have to do benchmarks in. I talked about this before with LINPACK and so forth. And here you have the list from the top 9. And you see these are really the cutting edge performance systems. You have here the supercomputer Fugaku with 7 million cores and quite a powerful footprint I was also alluding to. And then basically lots of different systems in the US and China, which are also very powerful. Different vendors, which is quite interesting to understand, IBM, HPE, which is indirectly Cray. It's quite a traditional HPC company, which was basically now acquired by HPE, but is known in the community since a long time. In Europe, we have Atos, basically. And here you see also that in number 8 on the list, you have this so-called JUWELS system. And here this name also is not surprising to you. I was basically saying that we in our research center basically have the good fortune to have access to so much computing. And now you would say that we are very lucky researchers that only Jülich can access it and has gotten so much money from the government to create so many good systems. And we had the Eureka system as well, which is lower in the list and so on. Now, the reality is that, of course, you have here many nodes. So let's look a little bit what the JUWELS system really is to better understand it. So you see already the picture says it all. It's quite a big system, many nodes. And when you go to the configuration here, you can already a bit understand perhaps the difference between Jotun, which had 4 compute nodes, and also the, let's say, CPU number was a little bit older, had 12 cores. Here we have 2 times 24 cores. and we have 2,270. And this is just the cluster module. I also talked about with the modular supercomputing approach. So here we have a cluster module, and if you scroll down, you have this booster module I was alluding to. So here we have lots of different of these compute nodes, and you will see in the booster nodes, you have also lots of compute nodes, but also a lot of accelerated nodes. The accelerators, GPU programming will come later in the course, but it also shows you that this is quite a strong system for scaling out, for boosting with this, let's say, as said, more moderate performance, basically processors that we call GPUs. And we will talk about this a bit more, and you can see that each of these compute nodes is basically less than you have above, but each of those is equipped with 4 NVIDIA A100 cutting-edge GPUs, which brings it to this high number of 3,700 GPUs. So in other words, this is a system for very many researchers. It's not for just the Jülich front. In Jülich in Germany, we actually provide this as a shared resource, not only on the campus of this Jülich research center, and also not only for Germany and German researchers, we provide this basically in the European level, previously under the umbrella of PRAISE, and PRAISE is unfortunately ending. It's basically a kind of infrastructure for computing, which is now transitioning more and more into something we called EuroHPC. If you remember, we talked about this as joint undertaking of all the European countries together in order to make a difference of, HPC and to unite the forces. But the key idea will not change. So people have to submit basically proposals in order to get access and time. And time means specific quota in core hours on these different systems. So this really is an important part, because when you go out of the course and go into production, always think not that these systems are for granted in academics. It is true that we don't pay for it. Basically, we pay in core hours, which means it is granted to us through grants. And then basically we can reuse these quotas then for our scientific research, for our engineering problems. And if you go to the cloud, of course, maybe here and there you have to have high costs. So I know, for instance, one GPU core, 1 hour here in GPUs, cutting edge ones could be, let's say, $24, for instance, in the AWS, in the Amazon Web Services here and there. So this is tremendous cost that we would basically never be able to pay as researchers. Hence, we need these free systems, but when they are free to us, that really means we share them with a wide variety of users. And to this aspect, I want to basically now allude to when it comes to scheduling. So a scheduler is now taking care of all these different compute nodes, of all the different login nodes. We just had Newton as one login node. You see a real production system in the top 500, number 8, and perhaps number 1 in Europe right now, is basically having 12 login nodes to manage the concurrent access. Many people want to access a system at the same time. And now this is something to realize then when we perhaps look a little bit more on a graphical representation of that. And this is a good example where maybe some of you, especially the PhD students here in the course, you have the chance probably once or twice, given COVID and so on, maybe to reach our systems in Jülich. And then the first thing you see when you come to the big machine hall that you have seen in the JUWELS system, you will see something like this. So this is the first and perhaps the most important screen you see when you come to the hall of supercomputers and look from above to it. And it already looks a bit technical, you can imagine, a bridge to science, so to speak, from thinking about that all these different colors are actually different users using parts of the supercomputer. And they can be using that, of course, in 2 different ways in a way. So one means that you basically have an application. You see here as an example, it's a so-called UNet in deep learning. The details on that is not important, but it requires quite some computing to basically compute this with remote sensing images, as you see a little bit here. And the idea why people then want to use HPC is, of course, as we discussed, doing parallel computing, and why they want to do this in order to save time, right? And to compute faster. You see here the time epoch in seconds, basically. And you see with more GPUs, you can break this down. And no matter you use this with JUWELS and the JUWELS booster, or you use this with a deep test cluster, essentially you see here that basically the key idea is to have more GPUs thrown, so to speak, on that particular problem in order to go with so-called speed up. And this speed up and the theory about it will be actually part of subsequent lectures. So we don't want to overwhelm you here now with the first part, but this is really something to think about. So at the same time, many people are using the supercomputer right now as we speak. And there's a so-called LL view that actually shows you this in this nice graphical overview on the one side. And of course, when doing so, you will imagine you maybe submit different tasks. You want to have 4 GPUs, 8 GPUs used, and perhaps there's no space left. So that's why another part of it is a certain queue. But this means also that basically in this multi-user environment, it is very now important that there is a software that manages all of this, right? As I alluding to before, and that one user of a HPC system even use many different tasks at the same time to be executed, right? So basically, of course, you would have also one job maybe only somewhere in the corner, but you can also have 10 jobs at the same time. And this is, of course, something I will show you a little bit on YouTube later, but also in a large scale system means there must be specific space for the job. If you want to use 16 GPUs, we maybe have to wait some time until 16 GPUs are free. So this is important to understand really. And this is a, let's say, zoom in into this. And here you see essentially all these different aspects of different users in this so-called queue and how they execute and use the system right now with a number of cores and so on. The details of this, who user it is, you can basically look as a monitoring tool here, exactly every detail up, how much memory is used, and essentially you will understand even where on the system you are. So from all these interesting racks that you see down here, you can imagine that you will be some part of it. And it depends obviously of how much you actually use in terms of resources, right? So these computational jobs are so much important. And of course, here we're talking just about the compute nodes. As we said earlier in the first part of the lecture, people use the login nodes to use a scheduling system we will come to in a moment to then do and execute these computations here on all these different nodes. And you will also see that the scheduling system not only has to manage all these different multi-users and multi-jobs, because everyone can have multiple jobs as well. Also, it has to deal with failure. So what happens if a kind of rack here, for instance, is out of duty due to maintenance? You see there's essentially not really a job anymore here. So this is basically, it protects from execution there, because essentially it's used for basically maintenance or whatever reason. Maybe there's an error somewhere in the network interface. Things have to be fixed in this particular rack. So also you see almost directly that what we aim for in supercomputing is, of course, to have a full utilization of the system 24/7. This is basically not really achievable to have 100%. That's why people talk about usually 99% uptime and usage, because of course there's always maintenance windows, there's some errors that you never really access the 100%. But this is incredibly important because these are unique resources, very, very costly. And of course, they should be used as much as possible, and not like our Jotun system that we have seen. It's a teaching system. It's a bit older. So basically, if we don't use it, it's not a big problem. But here we talk about the cutting edge systems. And here, #1 in Europe, which costs a lot of taxpayers' money, and people want to have results computed there and access on it. And as I said earlier, it's also very competitive. So you basically have to submit the grants in order to basically, and the proposals for grants to really get access to these systems in computational time. The other part to take away is a little bit, and that's also how this system is used often here in practice in Jülich. So we basically, you looked at also up in terms of the queue status. So this shows you the queue in the next, let's say, 24 hours. And you see there's already some jobs scheduled. We are right here at the blue part. But we see also that basically now there would be space enough to use this part of the system here. So I can also see how big my system can be maybe, or how long I have to wait, right? If I have a very large job, let's say the whole system that needs to be used, then I see I cannot be scheduled until I'm basically scheduled after this black user here on the bottom. So there's no space. But if I have, let's say, something which fits in the queue right here, then I maybe chances are that I got almost immediately scheduled. Of course, then on the other hand of the scale, you would say these big systems you don't use with a hello world with one core, right? Access to these systems usually is only granted if you have a code that really scales up, which use different nodes at the same time. Nobody is allowed to have, let's say, just a couple of nodes used here, because you will crack the schedule, right? You will basically hinder others to get bigger jobs done. That's why usually it's prevented to have very small jobs. And you will find basically not really jobs which have, let's say, the hello world character you have seen with 1 node or 2 nodes or 4 nodes or so. And with this, we basically have the foundation now. We basically understand that at one point in time here, really, this is a snapshot in time. This system is incredibly used by many different users, and it could be even that these different many users have multiple jobs in parallel on the system on different areas. So how we deal with this? How is basically HPC now coming to the point of managing this, which brings us to this so-called scheduling systems. Just to reflect, what you just have seen is just a monitoring system. So it's not really a scheduling system. It gets the information out of a scheduling system, like LLView takes it from the load leveler and now other schedulers. The ganglia that we have seen on Newton, if you remember, with these 4 nodes, basically from the first part, I will re-show it here quickly just for the people to understand that again. We said Newton here, the teaching cluster has 4 nodes, and when we go to the ganglia, you see this is also monitoring. So we can understand and look at the system. We understand right now there's, let's say, not much load, and probably in the next couple of courses and then assignments coming up, then it will be more loaded. Of course, here we can imagine that this will be going up. And this is what we call a monitoring system. It's an essential HPC system software to understand, is the system healthy? Is it operating well? I was alluding to this one rack which was offline. It's very important. Then also understanding the system load and so on. Of course, it's also nice, if you have visitors and show, hey, look at this supercomputer, it's nicely used, 99%. And of course, for our decision makers and the funding organizations, they also want to know the load of the system. So is it really used, or do we pay hell a lot of money and it's just, let's say, 40% used? Then we maybe can have smaller systems in the future. Hence, one of the goals is also, of course, to show decision makers, those that also are in charge of the funding organizations or public-private partnerships here and there that maybe also operate with vendors. And here the monitoring systems are, of course, also an excellent way to show that, but also give statistics to those and show that the system is, in an ideal case, 99% used. There are others like the performance analysis tools we will come to, and also the operating system. I was already doing a little bit basics with this with Unix environment. So let us come now to the other essential tool, which is a scheduling system, which is a core idea of our lecture. But the interesting thing of these systems is that they manage this concurrent access, this multi-users on a supercomputer extremely well. There are lots of these systems which are extremely, let's say, stand the test of time, so to speak. They are known since a long time. Torque, Slurm that we have on Newton, Load Leveler in the past with BlueGene. These were all really production systems which you can rely on, you can trust, and have here and there maybe smaller errors, but work like a charm. And we will explore this a little bit, how that looks now, basically, if we have the Slurm environment in Newton. And of course, one of your first assignments is to make that yourself, to compile, to use C programs, and then, of course, also go to the MPI space, which will come next in lecture 2. The idea how they work would fill actually a couple of lectures. So in fact, scheduling algorithms, scheduling theory is a research branch, so to speak, in HPC. So how you batch a system while not lowering essentially the future load, right? So you never know what users will submit at what point in time, and optimizing the system and the schedule becomes basically an NP hard problem, because you never know exactly what users will the system use, unless those that you have, of course, already in the batch queue. This is known, then the scheduler knows exactly in this queue, okay, they have submitted the job, as we call it, submit to the HPC machine, a kind of request for so many cores, and it's in the so-called batch queue. So you have to wait until you come home. Now, if there's space enough now, there could be things like backfilling we will discuss and so briefly. But the key message to take away is really that there are lots of scheduling algorithms and lots of theory behind it. But they actually, the scheduling systems now basically talk to all the processes and keep an overview of basically seeing the load, of managing when is a job completed, when it is running, when there's an error maybe. So these are all elements which are incredibly important of HPC system from the practical insights. And this also shows you another difference, perhaps a little bit to your laptop character, or basically for some of you that have operated Java, you know, in the past, and compiling Java programs and executing directly out of the IDE, the integrated developer environment or so, like Eclipse. This is different here. In software, in the area of HPC, many things are different. Some of them are very, you know, shared, like the use of libraries perhaps and so on. But here, when we talk about the access, we're really in a batch processing. So it's not anymore this really interactive way. There are now Jupyter and other interactive ways, but it's more used in basically the way of doing AI, and not for very, very large jobs. If you have a small job to experiment and so on, maybe, but the real way of using is usually through so-called job scripts. So these are scripts which basically have the application tasks inside, and where basically users will indicate in this job scripts what to do. And then the scheduler gets these scripts and then will execute it somewhere on the system where the scheduler believes it's the best. So basically it's out of the hand of the user. You just say how many resources you want, but you don't say, I want to be in JUWELS in the top right corner here, on the low left corner here. So here it's rather, you specify the amount of memory, you specify the amount of cores, maybe even the amount of accelerators. So, and then you are scheduled by the scheduler. And at the same time, of course, the scheduler acknowledges that you maybe have 3 other jobs already running, but it also looks at the other multi-users, what they right now doing. So basically dealing with this concurrent access to the system. And as I said, also has a different number of algorithms. Here's the first come, first serve queue idea of queues that really in the order how they arrived. I think that's very easy to understand. But sometimes you find a hole in the schedule and would say you can do a backfilling. That means that basically there's maybe free space and your job would basically fit, although you basically have submitted a job way later than others. But because your job can be right now scheduled and uses computer, it will be executed right away. So you're in a lucky position, so to speak, by filling somewhere inside this kind of unique spot. And by this can be, of course, be faster done with your job. So scheduling theory is not so much what we want to do right now. We want to come to practical examples, and that's exactly what I want to do right now. Again, we think about the idea now of Newton. We came back to the idea that basically what we had in the first lecture part. So let me clear a little bit and recap. We had our Hello C program, you know, very simple, just saying hello world. Then we basically have compiled this. We have loaded the different modules, modular GNU MPI. We have done then MPI CC and compiled this from Hello C. We got then an executable, which was then this green element here. Now, by basically looking at this, we also said, like, it's an executable now, we can actually use it. So let's do hello, but we also learned it basically is not the way how we operate it. And of course, you can repeat this, but we are always working only on the login node. And this is not what we want to do. Hence, we look now into a so-called job script I just was explaining, where you now tell the scheduler Slurm what to do. And for such a simple program, obviously, the script is very, you know, it is for Slurm, the script is very small here. So it was usually indicating the bash, the shell you want to use, but then also giving here an sbatch command in the script of saying -j is, for instance, the name. Sbatch -n means how many cores I want to use. Do I want to get notifications basically when the job has done something? And here we say this sbatch mail type at the end, when the job is finished, I want to get a message shortly from the scheduler to Morris@howie.is. So to my mail address. And of course, here you should add your own mailing address in the assignments and so on. And you can here have also start of the job and other elements. In the end, the sbatch command has lots of different options here that we will have also looked up in one of the next lectures when we differentiate, for instance, the capital N to small n nodes versus cores and all of these things a bit more. But for a simple starter script, we are almost there. Of course, these are just more or less meta commands for the scheduler to understand how much resources you need, how your job is named, how is your communication, but it doesn't say really what to do. Hence, we have to also think about what to do. And apparently, you can imagine now the idea is to recreate the module environment. So we have to execute again module load GNU OpenMPI. And it's now important to understand that basically what we've done in the login node is, of course, not valid for the compute node, where you now scheduled it. Once again, when you do sbatch and will basically send this script to the scheduler, you will land somewhere on some compute node where we did not put module load GNU OpenMPI before. We did this in the command line before and we compiled, but this was only the login node. The compute node has not seen these commands. That's why we have to specify those modules also again in the script here, because it will be landing somewhere on the compute nodes, and then there should be the same environment. There's another command called MPI run, which I use here just because to have an easier transition later then to our MPI programs, which also then brings this parallel run really out to the cluster. And that's what we will start in lecture 2 to explore this a little bit better, to have really parallelization done and so on. So I don't do this here in this part of the lecture because we just want to understand roughly the scheduling. And then we will come to, let's say, the 4x execution and so on different cores and parallel computing in lecture 2. So in other words, what we've done with this script here now is we transformed this normal command line command .hello to the correct way of how to submit to a supercomputer, right? And this is a typical, let's say, script file here. So we can go out of this. And you see here, of course, the path to the hello, right, to the executable, which will be then used and which would be compiled. We don't compile there anymore. We assume the executable to be there. And this is this kind of interesting batch script. It remains basically a typical batch file, text file, but because it's a shell script, in the end, you can call it .sh, and with this, you know, basically have also a status of executable. But that's also not how we really use it. We will do a certain command that I also have looked at basically in the slides for you. So don't worry, everything which I will also do here in practice, I will also show you here on the slides what to do. We basically do a so-called sbatch submit hello. And let's do that first to understand it a bit. Sbatch, which is a command of the Slurm scheduler for basically now telling the scheduler what to do. And obviously we take here our submit hello.sh job, and actually we get a job ID back. This batch job ID with this particular ID, which is important because it identifies our jobs. And now we wait and can see with QStat if the jobs are running. And now you see that the hello example that we have with this particular ID is done. It's already completed. The time used was very, very little. As I said earlier, it's not really a tough job, right, to just put hello world out. But you also see with submitting this, we don't get any output. And this is weird, isn't it, for normal users, where you said we did this .hello, we got our output, and now where's our output? We submitted it, it is completed. And you can, of course, influence where you put the output. But in, let's say here in the course, in the first part, you will see that where you submit it, you also will get into this directory a slurm minus job ID, what we just had here, out. And no surprise, what you would expect to have therein, if you use more, for instance, with this particular one, this is now, of course, important. This was our file. Surprisingly not, there's hello world. So, but now important to understand is the whole approach. So that's why I have to go again to this, to really understand this now, why it is a remote execution on these different compute nodes, right? So what we did was we had the submit hello world script basically looked at in the login node. We basically looked and can modify it. For instance, you please send the email to your own emails, not to me, otherwise it gets spammed by jobs. We have looked at the queue status, and in the moment you see that queue stat was pretty empty, right? So interesting enough, there's nobody using the system right now except me. This will change. So if you all different users here from the students and do your assignments, you will see that the queue stat will grow with different jobs. And also what I wanted to say is, and I can demonstrate this as I was alluding to earlier, no one prevents you to have maybe different jobs or many jobs on that, right? Like here, I can do now this and this and this. And what you see suddenly is a queue stat with lots of Morris jobs. Of course, here, this will be different student jobs, and you can imagine executing the same many times usually don't really make sense. You would twist parameters, you would change and maybe program or debug a certain software, then resubmit. But here now you have seen that at the same time, my job was running on many different cores and all essentially came to some output. So you see now, basically nothing is written yet in the output directory, but very soon we assume that all these different job IDs, which are here, so the first one is already done, will basically also written to disk here. And you see here it's happening. They're all from the same size. So I spare you, of course, now looking into all of them. We maybe just take the last one just to double check if it's still hello world. And this now showed that basically we are ready to submit a job on HPC systems. We have seen the login node was only involved for compiling and then for the submit as batch command itself. And this is the way how you use a supercomputer. There are more commands like canceling jobs. You can have more statistics on this QStat to look below different examples of different users. The time elapsed, of course, you will see here sometimes the scheduling in running when you have long-term jobs like 24 hours or so. Obviously, this is the first baby steps we do here. But what it really helped was to do it in the right way, right? And now wherever you go in supercomputing centers around the world, you will find that this is the right way. You log into a login node. You have seen JUWELS has even 12 login nodes to manage the load of all these users, but they do the same way. They compile, they prepare jobs there in job scripts, and then they use some form of a scheduling script in order to go to the compute nodes, which are different than the login node. The JUWELS systems we have seen, they are even accelerated in the booster, for instance. Jotun don't have that. It has only 4 also. This is a, let's say, just a picture. So essentially we don't have 6 nodes, we have 4 nodes. And then in subsequent ideas now of lecture 2, practical lecture 2.1, we will see how to use essentially the good interconnect I was alluding to in the later parts, basically of the introduction and also of the prologue and so on. What makes it really HPC system is that we want to communicate among these to use really basically these parallel systems in a parallel cooperative way for one application. What we did now was merely throughput, right? We had the same application running here on all these different nodes saying hello world. It's not a big deal, but it shows you the key essence, essentially how a supercomputer is used, also JUWELS, not only Jotun, and that we have output files which are not directly visible on your screen on this device, rather written into some form of an output file. And of course, this output file don't have to be text only. If you have, let's say, a point cloud, if you have data items, this output could be also non-text. It could be directly written binary back in a so-called parallel file format, which we will learn also step by step now, going through MPI, understanding MPI IO, and then coming to parallel IO in the subsequent lectures. And then basically over the course, I would encourage you to always monitor this with QStat, to basically program a little bit here and there in the assignments. Of course, we will keep it to a moderate degree with C programming, right? This is not a programming C course. This is a power computing course, HPC. So we will put the emphasis here much more on using really in a parallel way a supercomputer instead of making it beautiful in programs and so on. Of course, we want to have still correct programs. And of course, here, the idea is that MPI or correct MPI programs in a way are also correct C programs. And we'll basically then look from the next basically lecture, when we have lecture 2 on these systems. Of course, one short takeaway message: you have to be incredibly careful if you do some things. Just for the sake here of showing you also what not works is, of course, if you be a bit sloppy and say, well, we had here somewhere this executable in this path, and I think it was called hello, but maybe it was also called hello in capital, right? Now, this is something where it's dangerous. You're in a Unix environment, remember it. And also shows you that the scheduler can also deal with error. So we submit now something which is a file which don't really exist, right? So in this sense, what we assume is that we still get some output, hopefully, and check if the job was running at all. But it was running, so this is good news for us, and it's already computed, okay, but there might be an issue with it. And we basically will see that perhaps not really the executable was found. So let's look into the one that we just submitted. You see here also sometimes it can take a little bit of time of I/O to really write the output file. So here you have to be a bit patient, and suddenly we see also much more characters in. There's some trouble, and we know why, I mean, basically between us, but let's look how the scheduler is basically thinking about this. And here there's a nice example that you basically see it could not access the executable. It's correct. It is not in capital. It's actually just in small letters. And you also see compute to 0. So we can reflect that the scheduler put it in the compute 2.0, which we know. When you look on the UTune, here basically at the glance in this report, you remember we had the chance of basically going to UTune and then choose a node. And there was this compute 2.0. So we can directly see that basically we have been scheduled on this, and then basically the scheduler wanted to just execute what was written there and failed, right? And rank 0 is something which we will allude to the next time when we talk about MPI ranks and what that means to distinguish different ranks in MPI. So we don't do this all at once here. But here you see basically this nice example that there is also an output showing you the error and also actually where it happened, what happened. That gives you a chance to debug. And in our case, we probably want to rename this again. So here's a quick way of doing this. When you go to this submit script again, let's go back to the small hello. And that's really all I wanted to leave you on the table for this lecture. Obviously, there's much more to learn. We will look in the whole HPC lectures much more into these commands for the SBatch. For this Learn Scheduler, we will use different modules and then also different, let's say, cores, which are really working in parallel. In a way, we tweaked this here today a little bit and faked the parallel computing in the sense that we did Hello World several times, but it was never interacting. It was never really one program. It was different programs submitted and they were run at the same time. But sometimes we will change this, and we start with this in lecture 2, and then practical lecture 2.1 will show you how we use it in the assignments. So thank you very much for joining us in this more practical lecture today. And I encourage you to really try this out practically on your own. Only then you get basically, fluent with using batch systems, with the batch scripts, the C programming part. It works almost the same way for C# or basically C++ programs and Fortran programs. The same scheduling scripts have to be written, but then obviously you basically execute Fortran programs, and other modules have to be loaded for understanding Fortran and so on. But the basic idea should be clear by now. That's all for today. We basically continue with lecture 2 the next time.